Okay, here we go. So, like I just mentioned, this first chapter. So let's go here, maybe chapter 0. 0 is also a number. So this will be a review. For shear and bending moments. Diagrams. Okay, so the first thing I'm going to do is to go through the procedure with you. And if you take any class with me, all my procedures are basically the same, okay? No matter what is the first thing you need to do in a problem is always to do some type of figure or sketch of what you're trying to solve. Let's say figure. So, second step, in most cases, you will have to find the reactions at the end of your beams, no, or your structure. So, will be to find the reactions. So, in order to find the reactions, what do you need to use? You probably need to use the static equation. Summation of forces equal to 0. And summation of moments equal to 0. Three, using the shear and bending moment equation, which I'm not going to rederive, I'm just going to give them to you. Okay, so you're going to determine the shear force and the bending moment. So from here, you're going to find shear force and bending moments along the length of the beam. So it will be in function of x. So for that, what do you need to do? You need to, the rule is that you need to make a cut every time there is a discontinuity in the loading. Okay, if it's not clear, we're going to do an example. I hope everything will be clear. So once you do the cut, again, you're going to have a figure. And again, you need to apply here. So if you want letter A, letter B, you use summation of forces equal to 0 to find the shear V in that section. And then you apply the moment equation about the cut in order to find the bending moment. And last, once you have all the equations for shear and bending moments, what you can do is you can sketch shear and bending moment. Okay, so this will be the diagram. All right, so just like I mentioned before, I'm going to give you the equations, the shear and bending moment equations. So equations here will be what? So there's one, which is dv dx equal to W, where V is the shear and W here is the distributed force or distributed load, whatever you want to call it. And then there's another one, the equation, which is dm dx equal to V. Okay, but personally, when I solve for the shear and bending moment diagrams, in most cases you don't need these equations. Okay, it's just if you want to do it more mathematically, but if you want to do it just using the understanding, you don't need these equations. All right, so let's do one example. All right, so example. Let's say we have a beam that is simply supported at this end over here. Here is a roller support. And the loading on that beam, we have a distributed load between these 2 points. That is equal to 6 kip per foot. And we have a punctual load at the end, P here, equal to 5 kip. And this is point A, B, and C. The distance over here is 8 feet. And this one here will be 6 feet, okay? So what's the question over here is to draw shear and bending moment diagrams. Okay, before doing that, maybe let's do a little review about the boundary conditions. If you have these boundary conditions, how many reactions do you have? You're gonna have, so let's say this is point A, you're gonna have a reaction on the Y, and then you're gonna have a reaction on the X. Okay, so this is simply supported. Now, if we have this one over here, which is a roller. In this case, how many reactions are you gonna have? You're only gonna have one on the Y, no? Okay. And now if you have something that is fixed or clamp, so let's say fixed, so it would be something like this. How many reactions you're gonna have? You're gonna have a Y, a X, but you're also gonna have what? A moment MA, no? Okay. All right, so let's go back to the first page that we had over here. Now we're ready to start. First thing we need to do is to do what is a figure, no? All right. Oops, now just so, let me complete it now. It looks like I did not finish to say, I started here to say that V was the shear. So let's say here N will be the bending moment. Okay, and that will be it. All right, so first step to do a figure. Second step to do the reactions. And then to find the shear and bending moment. All right, so yeah, maybe I can just do it in here. So let's do here, step one, free figure / sketch. So what do we have? I have here point A, point B, and point C over here. So we have A, B, and C. So how many reactions I'm going to have at point A? This is simply supported, so that means we're going to have two reactions, AY, AX. Point B is a roller, so how many reactions are we going to have? BY, just one. Now we have the force P over here of 5 kip. And now we can replace, just to find the reaction, we can replace the dissipated load by just one force acting in the middle, no? So the value of this force will be what? 6 times 8, which is 48, okay? So one force 48 acting in the middle over here. So 6 times 8 equal to 48. And what will be the distances over here? So let's say this will be 4 feet. And this will be 6, no? All right, so now that we have the figure, what can we do? We can find the reactions. In order to find the reactions, what do you do? Summation of forces equals to MA, summation of moments. So basically this is statics, okay? All right, so you need to keep the figure in mind over here. The last one. So 2. We're gonna find the reactions. All right, so let's follow the order. Let's first do summation of forces on the X. So again, something you need to know is that equations do not appear from magic. They always come from some type of figure, no? Okay, so in the X, what are you gonna have over here? You're gonna have AX equal to 0. So if we follow a procedure, let's say this will be your first equation. Next thing we can do is summation of forces on the y equals 0. So this is going to give you what? A y plus by minus 48 minus 5 equal to 0, which simplifies to a sub y plus b of y will be equal to 53. And we could say this would be our equation 2. So obviously here you have one unknown is 0. Here, how many unknowns do you have? 2, a y, by. You only have one equation, so you need to find another equation. What will be that additional equation? Summation of moments equal to 0. But what is something specific about the moment equation? It's always about a point, no? Okay, so in this case, what would be the easiest one? Probably point A, no? Because you eliminate at least one of the variables over here, a y. So you need to specify about which point. To me, if you put a moment equation without a point, I'm not even going to look at the equation, okay? You need to define that. Then also what I like to see, but that one, if you don't put it, I will assume the normal sign convention, which is what? A positive moment is counterclockwise. All right? Okay. So this will give what? So let's say we have the force 48 times 4 feet. Is that one clockwise or counterclockwise? That one is going clockwise. So that means that this will be a negative moment. Now, by will be going counterclockwise. So that one will be positive. So plus 8 b sub y. And then with the 5, that will be what? Going clockwise. So that will be negative minus 5 times what will be the distance? 6 plus 4, 10 plus 4, 14. Equal to 0. So this will give you that 8 b sub y is equal to what? So let's see, 5 times 14, that will be 70 plus 48 times 4, so that's 160 plus 32, 192. So, but if you have your calculators, please keep it out. So this will give you by equal to 262 divided by 8, which is okay, 32.75 kip. So now that you know by, what can we do? We can go to equation 2 and solve for a y, no? Let's say here from equation 2, we're gonna get, so a y plus by equal to 53. This is gonna mean that a y equal to 53 minus by, or a y will be equal to 20.25, no? Yeah, double check, please, but I think if you add here 20, you get 52 plus 75% would be 53, so 20.25. Okay. Okay, so if we look to the procedure, we did the figure, We found the reactions. Now step 3 is to find the shear and bending moment equations. Okay? So step 3. Shear and bending moment equations. Okay, here I'm going to redo the figure very quick. So we are here A. I think here we have the roller. And here the force. Okay, so I have here distributed load. Here we have the force of 5 kip, 6 kip per feet, and this was point A, B, and C. Okay, and we knew this was 8 feet and 6 feet. Okay, so on the first page, what did I mention? Now that you have this, you need to start from one of the ends. So in this case, let's start by the end point A, and you need to do a cut every time they say discontinuity on the loading. So how many cuts are we going to need? We need 1 cut, somewhere between 1 and 2, no? Because here's uniform, 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 but right before getting to 2 is going to get a reactions, no? So it's not going to be continuous. So you need 1 type of cut over here. And then we need some type of other cut over here, because here is going to be uniform, 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 but then at the end it's going to be discontinuous because of the 5 kip force. So we need a second cut over here. And once again, we go back to the normal procedure, which is always do what? Now, for the first cut, you do a figure, you apply summation of forces, you apply summation of moments. Okay? Always the same thing. All right, so for the first cut, maybe I can do that in, let's see, first cut, which is what? Between x equal to 0 and x equal to 8, not included. Okay, so letter A will be to do what? Some type of figure. Again, I do this time for the first problem. After that, I'm not going to redo all these 1, 2, 3 and little detail, no? Okay, maybe I do it, but not in that much detail. But so figure. So for the first cut, what will be the figure? So I magnified a little bit, so it will be the cut over here. So we start from this point over here. This is point A. So what do we know about A? We know that AX here was equal to 0. We just calculated. We calculated AY to be equal to 20.25. Okay, and here we have the load, the distributed load. To be 6 kip per foot, and this is the cut. Okay, this is where we did the cut. So because we did the cut, what's happening? You're gonna have a shear force V1 appearing and a bending moment M1 showing. Okay, conceptual question. Why do we make a cut? Let's see if anyone knows. So why do we need to make a cut? All right, because the internal actions, shear and bending moments, those are internal actions, okay, within the structure. All right, and you know that by Newton's third principle or third law is that every action has an opposite reaction. Okay, so if you don't make a cut, it's like here. Why do we remove the support? We remove the support A and we replace it by two forces, no? Because if you leave the support, the action of the within the support is going to counter-react the force of the beam, no? But now, if you remove the support, you need to replace the support by two forces. Yeah, okay. So it's about the same thing. If you want to find the shear force inside the structure and the bending moment inside the structure, the only way to make those forces to become external will be what? To make a cut. And that's why you do it, because otherwise you cannot use summation of forces or summation of moments. So that's what we did over here. So by making the cut, what's happening now? Those internal actions that will be shear and bending moment become external. So you can put them on the figure, no? Now that these two become external, what does that mean? We can use summation of forces and summation of moments equations, all right? So we use the summation of forces to find V. We use the summation of moments to find M, all right? So that's what we're doing. So B, let's find the shear equation. So for that, I need to specify one thing. Here, we said this will be X. So if you want, this is X. Okay, coordinate system X along the length of the beam. And let's say this will be Y, if you want to be specific, okay? So the shear force, is it on the X or Y direction? It's on the Y direction, okay? So in here, there is no forces on the X, no? What will you have? You have AX equal to 0 equal to 0. So we don't need it. But if you had forces on the X, you will have to apply it. Here, there's only forces on the Y. So we're going to apply summation of forces on the Y equal to 0. So again, all the equations come from figures. So figures are very important. So what are the forces on the Y? Will be AY minus what? Minus 6, which is acting over what distance? X. Perfect. Minus V1 equal to 0. So now we can solve here for V1. That will be in function of X. So V1 will be equal to what? Minus 6X. And AY was 2025 plus 20.25. So here we have the first equation for the shear force that we obtained from summation of forces. Okay, so if we want to plot this figure from X equal to 0, we're going to need 2 points. So let's see. So this is the equation of a straight line, no? X. In order to draw a line, what do you need to know? 2 points. Okay, so what would be the easy points? V1 of 0 will be equal to what? 20.25. And what is the other point we need to know? At what distance? Probably the best option will be to see what is the value of V at point B, no? So that would be what? V1 at point 8 will give you what? Minus 48, 20, 27.75 minus. Okay? And all these units should be kept over here. All right, now from this figure, we do exactly the same thing, but this time we're going to take the moments about the cut. Okay? You could take it about point A, but just always do it about the cut. It's easier, okay? All right, so we take moments. So we find the shear. C, we're going to find the bending moment equation. All right, so we do summation of moments. About the cut. And you need to define the direction. Okay, so from the figure, what would you have if you take moments? So let's start by AY. AY will create what? A clockwise or counterclockwise? We create a clockwise moment, no? So that should be negative. That should be minus AY times, what will be the arm? X. Good. So now let's say plus, before I forget, I'm going to put M1. So we took the action of AY, we do M1. Now we need to see what would be the moment created by the force CX, no? So we could replace, what would be the value of this force? We can replace this one by 1 in the middle, no? What would be the value of that force in the middle? Would be, so 6x will be the value of the force. With that one, create a positive or negative moment. Would the moment about the cut be clockwise or counterclockwise? It will be counterclockwise, no? So that will be positive. So this is the value of the force. What would be the arm? What would be the distance from here to here? X over 2. Okay? And that should be equal to 0. So basically at the end, what this is going to give us is what? M1 will be equal to minus 3x squared plus AY, which is 20.25, so plus 20.25x. Okay, so now, what type of equation is this? This is a quadratic equation, so probably we're going to need how many points to define it? If for a line which is in power x, how many we need? 2. When it's something to the square, we're going to need at least 3 points, no? Okay, so like before, maybe we can do the easy ones. We'll have, let's see, what color did I use? Red. So we have M1 at 0 and M1 at 8. Will give you what? M1 at 0 will be 0. M1 at 8. No idea. Let's see if you can do it. Negative 30. And this is kip per foot. Okay, so what type of equation is this? This is a quadratic equation. So basically it means that it's either gonna be this way or this way, no? So we need to find the point where it's gonna change directions. How do you find the point where it changes direction? Calculus 1. You need to take the derivative, no? Okay, so let's say we do here, let me change colors. Let's do dm1 of x dx equals 0. That should give us the location. So what do we get? We get minus 6x plus 20.25 equal to 0. So that means that x is equal to 20.25 divided by 6, which is how much? 3.75. 3.375. Okay. All right, and yeah, we'll do that later. So basically, we got everything for M1 and V1. All right. So now we are here. Now, what do we need to do? We need to take care about do exactly the same thing again for the second cut. Okay. So let's see what was the presentation I used for the first cut. Reactions. Should have it here. Okay, first cut. So let's do the same procedure here. Second cut. This time will be between what and what? Will be x will be between 8 and 14, not included, okay? And okay, I cannot keep both things on the same page, so 14. So same as before, we need to do the figure. So I'm going to do the figure here. So this time at the end, we'll have here V2 and 2. So this is point A over here, where we're going to have the X. Let's say it will be point B over here. All right. So 8 to 14, 0 to 14. This is from, okay. With the second cut is between 8 and 14. Okay. The figure I'm going to do is from 0 to X. Okay. So what do we have over here? Here we have the dissipated load. Because you need to take that in good consideration. What is the value of that one? Is 6 kip per foot. Now we knew AX is 0. AY is 20.25. Then what did we know as well? BY here was equal to, let's see, 32.75. And this is here the second cut. Okay. All right. So again, now if we do letter A, will be to find the shear. What is the equation we're going to use? Is the summation of forces, no? So let's do letter A. We need the figure. Shear. What do we have? So we do summation of forces on the Y. What are you gonna get? Okay, you're gonna get AY. If I start from the left, we're gonna get AY minus what? 6 times 8 plus dy minus v2 equal to 0. So this will give us what? v2 equal to ay, which is what? 20.25 minus 48 plus 32.75. So this gives you that V2 is equal to what? So let's see. This will be what? 40. This will be 53. 53 minus 48 will be 5. Okay. Okay, so this one is constant over here. Okay, now B, we need to do the same thing for the bending moment. So we do the same thing. You take the moment about the cut. Counterclockwise positive. So what are you gonna get? So let's see. Let me start with M2, that way I don't forget it. So M2, and now move to the left, okay? What will be the moment created by the force AY? Now we go clockwise, no? So let me put the positive value. So clockwise will be negative. So it will be minus AY, which is 20.25. What will be the value of the arm? X is all that distance over here. Okay. Now let's look at the one of the BY. BY will also be create a moment going clockwise. So that should also be negative. Minus 32.75. So this is the value of the force. What will be the arm? X minus that distance, no? Yeah, which is 8. So X minus 8. That distance between A and B is 8. Okay, 8 feet. And now the moment created by the dissipated load, so that one will be now, we can replace this force by one in the middle of value 48. Okay, we know 6 times 8, 48. So that moment will be positive. And now what would be the distance between this force and this one? Will be X minus 4, no? Yeah. So X minus 4 equal to 0. So if we do the algebra, I have here the result, but if you want to check, for this one I had it, so you can check it, is 5x minus 70. So again, this is the equation of a linear of a line. So how many points we need? 2. So, and this cut is between 8 and 14. So probably the best choice is to do 8 and 14. So for 8 will be what? Negative 30, correct? And for 14, that will be 50, 70 will be 0, no? Which it should be 0. Otherwise, we'll have something wrong. Let's see, why should it be 0? Even why should it be 0? This is the problem. No, that's not the problem. I mean, it is a problem, but it's not the page I wanted to show here. Why should it be 0? Because at this end, the moment will be 0, no? Yeah, and this is more understanding, okay? All right, so it looks like now we have everything we need in order to do the problem. So you see we did 3, 2, 3, 4, 5. Let's do a little summary of result, okay? So this will be step 4 now. We need to sketch or draw / draw shear and bending moment diagrams. Oops, I think I had this one in green on the other ones. It's not a big deal, okay? So let's do a little summary of results. So let me use the blue maybe here, summary. So what do we have? We had V1 equal to minus 6x plus 20.25. And we knew here that V1 at 0 was equal obviously to 20.25, and V1 at 8 equal to minus 27.75. Then we know that V2 is constant, is equal to 5. Okay? So this will be for the shear. Next, for the bending moment, what do we know? M1 equal to minus 3x squared plus 20.25x. And we needed 3 things over here. So we knew M1 at 0 equal to 0. M1 at 8 equal to minus 30. And we knew that dm dx equal to 0 at x equal to 3.375. So we knew those 3 things over here. And what do we know about M2? M2 is equal to 5x minus 70. And here we know that M1 at 8 is equal to minus 30 and M1 at 14 is equal to 0. Okay, so over here, I would do 3 figures here, but I'm just going to do 2 because of the space. Generally, I would like to do this figure here on top. If you have space, do it very quick if you want. Okay, just to show the similarity. And then what I'm going to do is that I'm going to start from this end over here, and I will do something like that. Okay, and I will just do like this will be V with respect to X, but it would be Vx, and then I will do something similar again here for M. This would be M X. I probably will say this is point A. Let's say A. This is B, and this is C. I know it's not to scale, but it doesn't matter. We'll have to do something like that. I don't know how far it's going to go, but okay, so now we'll go and plot V1. What is V1? V1 is at 0 is 20.75. So let's say this point here will be 20.25, sorry. And we know at 8 is minus 27. So let's say at this point here will be minus 27.75. What type of line is that? This should be a straight line. Then what is V2? Second cut. V2 now is 5. So what does that mean? We have a discontinuity here. That's why we needed to make 2 cuts. We're going to go from 0 to 5 all the way up to 0.6. So this is 5 over here. So if you do the figure, this is what you get. Okay. Now, because I did not select it to use the equation, but what is this point? What should be this point here? How did we find the maximum of this one here? dm, we did dm dx equal to 0, no? Yeah. But also, what do we know? dm dx equal to v. So that means in this case, what is equal to v? So this is v equal to 0, no? When will be v equal to 0? At this value here, no? This is v, no? So really the maximum, if you look at it, the maximum of this equation will be located at the same point of intersection here. So we know this will be x squared. So if we do now m1, what is the expression for m1? Minus 3x squared plus 20.25x, m1 of 0 is 0. So we start from here. And then m1 of 8 is minus 30. Can somebody do very quick? How much will be m of 3.375? How much? 34.17. Okay. 34.17 will be this point. So basically what's going to happen, we're going to go from 0 here to minus 30 over here. So we'll have probably something like this. Okay. And then what would be M2 is a straight line. M2 of 0 is -30, and we need to go up to here to 0. So from here to here, we should have a straight line. Okay, and this will be the shear and bending moment diagrams. Okay, so why is important to know the exact equation for the bending moments, M1 and M2, is because if you want to find the deflection curve, you need to know those equations. So I'm not going to do the derivation again of this equation. I'm just going to give it to you. But if you want to be able to find the deflection curve, you have second derivative of dy dx squared equal to m. So this would be function of x over EI. So what is the deflection curve? So let's say if you have a beam, let's do a simple case here of simply supported. Okay, and there's a load. What would be, and let's say there's a load, a force right in the middle. What would be the deflection curve of this? It would probably look like this, no? And this is what would be y of x. So this will be x. This will be y. So basically, it's the equation of this curve. The deformation curve will be the equation of this curve. Okay. So that means what? That if you want to find the deformation curve of this one, what do we need to do? We need to integrate twice this one, no? Twice this equation. And the m here is, the m here might be different if you have multiple cuts. Okay, so probably we won't finish it today, but let's try to set it up. So so let's say here for the previous example, let us determine the deflection curve. Okay, so let me redo a figure quick. To me, I need figures. Without figures, I'm lost. So there's the figures. We had here point B. This was the distributed load. We had here the load of 5. I think this was 6 kip per feet. This was 8. This was 6 feet and feet. And what did we know from the previous example? We knew that M1 of x equal to minus 3x squared plus 20.25x. This was for x between 0 and 8, not included. And then we had M2 of x equal to 5x minus 70 for x between 8 included to 14. And this is A, B, and C. Okay, so basically, what does that mean? We have a different form. M1 is between A and B, and M2 is between B and C, no? Okay, so let's over here for segment AB, which basically is for X between 0 and 8. What are we gonna have? We're gonna have the equation D derivative of Y for the segment AB dx will be equal to M1 of X divided by EI. So this will give what? Second derivative of Y segment AB dx will be equal to 1 over EI. What is M1 is minus 3x squared plus 20.25x. So if we integrate once, what are you going to get? 1 over EI will be equal to what? Minus 3x3 divided by 3, no? So this will give us minus x cubed plus 20.25 divided by 2. It's going to be easier for me to type it down. X squared. But then what happens when you integrate? You have one constant, so plus C1. Now, it might or might not be important, okay? But let's say, what is the physical meaning of this term over here? What is dy dx? Is the slope, no? Okay. So basically, this would be the angle of the slope. All right, and if we integrate, we need to integrate once more. So if we integrate once more, we get y AB of x will be equal to what? 1 over EI factor of minus x to the power 4 divided by 4 plus 20.25 divided by 6 x cubed plus C1 times x plus C2. Okay, let's see if I can find the equation for segment B and then we finish it next time. Now we do exactly the same thing for segment BC, which is for x between 8 and 14. We're gonna have derivative of y BC dx equal to m2x divided by EI. So I just do exactly the same thing, okay? The derivative of BC dx. What is M2 is right here. is 5x minus 70. We have 1 over EI 5x minus 70. This will give us again the slope dy bc dx. We integrate once, 1 over EI. Okay, sorry. So now you can see, we give it what? 5 over 2x squared minus 70x plus a new constant that this time I'm going to call C3, not to mix it with the other ones. Again, this will be the slope for this section, and YBC of x will give you what? 1 over EI of 5 over 6 x cubed minus 35 x squared plus C3x plus C4. Okay, so now this is the last thing I'm going to write for today, but it's quite important. So now what do we need to do? We need to determine all those different constants, no? All right. So next, the constants of integration C1, C2, C3, and C4 must be determined using boundary conditions for their deflection curve.